Okay, we are recording. Hunu, the next exam is going to be on Wednesday. It'll be posted the evening of Wednesday, July 7th. Wednesday, July 7th. All right, no problem, no problem. So I think you've already seen functions of several variables. And one of the famous examples, and you've seen this in let me just see. I think you saw this in section 9.6. Let me see. Hold on. Yeah. Well, no, in 9.6 you saw wave height as a function of speed and time. But another famous example is wind chill index as a function of air temperature and speed. Okay, so here you have in the going across there, you have the speed of the wind, and going down, you have the actual temperature, and wind chill is a function of air temperature and speed. How many have heard of the wind chill temperature? The wind chill. Charles remembers that. Charles knows that. Ian has. Yeah, and so like for instance, and Andrew has, and you can see like if what happens like if the temperature is 5 degrees and you move and you increase the wind speed, what happens to the wind chill? So look, keep the temperature at 5 degrees and move then along, increase the velocity of the wind. It gets colder, and you can see the temperatures go from like 4 degrees to 3 degrees to 2 degrees, all the way like when the speed of the wind speed's 80 kilometers per hour, there you got -3 degrees as your wind chill temperature. So you see, wind chill temperature is a function of two variables. You can't just say wind chill temperature is a function of one variable, like air temperature. It's much better modeled when you include air temperature and speed. So this is a reason to talk about functions of two variables. And also in terms of economics application, because I know some of you told me that you are economic majors, there's something called the Cobb-Douglas production function. Okay, so Cobb-Douglas, they considered a view of the economy in which production output is determined by amount of labor involved and amount of capital invested. Now this is back almost 100 years ago, but the function there is the production as a function of labor and capital equals B times L to the alpha power, and K times K to the 1 minus alpha power. Okay, and they say here that P is the production, L's the amount of labor, and K is the amount of capital invested, like machinery and so forth. Okay, and so these are exponents. L and K are raised to an exponential power, and the value of the alpha, I'm looking there, that's in the exponent there, the value of alpha it would have to be given in the problem. It would have to be given to you. Okay, but the point is, would production increase if labor increased? I mean, looking at this in Formula 1 there, looking at that model, does it make sense that production increases with labor? It does. And production increases with capital. The more investment you put in machinery and buildings, production should increase. Yes, and so you see there's a multiplicative factor. You're taking labor times capital. Now you have exponents there, but it's kind of a combined effect in a way. So that's the Cobb-Douglas function, a function of two variables. So you can see it's important, these functions of two variables, to talk about them. All right, and in example 3, of course, here they want you to find, okay, whenever we talk about functions of variables, we always have to talk about domain and range. So here you have a function g of xy equals the square root of 9 minus x squared minus y squared. Well, the domain, of course, the domain that under the square root you have to have values 0 or greater, and so the domain would be given by x squared plus y squared is less than or equal to 9. Okay, so that's your domain of this function. And the range of the function would be all values, all z values. So z is equal to g of xy. All z values where the xy coordinates are in the domain. Okay, so that's a domain. That's a range. Okay, and you know, we can graph these functions and get an idea of normally of what they look like. If we were to, well, are there any questions on this example? This example 3. Okay, okay. Well, so many times we want to get an idea of what a function looks like, a function of two variables. And there are ways to help us do that. Now, of course, and by the way, there's the picture of the domain for this, this example 3 that we looked at. Okay, let me continue on here. So many times we want visual representation of a function. So here they say, you know, sketch the graph of that function in example 3. G of xy equals square root of 9 minus x squared minus y squared. Okay, well, if you, in the solution, if you just square both sides, well, first you set z equal to the square root of 9 minus x squared minus y squared. And then if you, and I'll highlight this, let me highlight this here. Yeah, if you square both sides, you're going to get z squared equals 9 minus x squared minus y squared, or x squared plus y squared plus z squared equals 9. That is an equation of a sphere with center at the origin and radius 3. But since you have a positive square root, z has to be greater than 0. And so g is just the top half of this sphere. Okay, so this is a picture of this function g. Okay, is there anything any questions on that? All right, and incidentally, the Cobbs-Douglas function, if we looked at the Cobbs-Douglas function here, and we let like L be raised to the 0.75 power, labor is raised to the 3/4 power, and capital is raised to the 1/4 power, this would be an idea. This would be what that function looks like. Okay, you can see the function values increase with labor and capital. So this is relevant to economics. Who are our econ majors? I think there are 2 of you, right? Who's an econ major here? I think there are, I thought 2 of you said you were econ majors. Maybe it's in my other class, but I thought it was this class. How many like economics? Okay, oh, so Ellie said she used that function in an econ class. Okay, there you go, there you go. So, Okay, well, what's one way to visualize functions? Well, one way is to use what's called, and I'm showing figure 4 here, to use what's called a contour plot. Okay, a contour plot. So, look at what they've done here in figure 4. You have this function of two variables. And what they do is they slice the function horizontally at different levels. And what's the difference between each level? What's the difference between each level? So the levels have different heights, and it does look like a topographical map. In fact, it is, in a sense, that red graph there in the XY plane. The change of Z is like in those levels, those cuts that they're cutting this function at different levels, and then they're projecting those levels down into the XY plane. So what are the levels? I mean, what are the different levels at? What's telling you what the different levels are at? The function is, okay, Z equals K. That's right. That's right, Hunu. So what's the smallest cut? What's the, the smallest cut is Z equals what? Or f of xy equals what? F of xy equals 20. That's right. And then the next level curve, or I should say the next cut, is at f of xy equals what value? 25. Good. And then the next cut is when z equals 30, z equals 35, z equals 40, and finally z equals 45. So they're skipped. These are, and then what they do is when they cut that surface, they take the cuts and project them down into the XY plane, and that produces what are called level curves. So essentially, you can get an idea of what your surface looks like by looking at the level curves in the XY plane. The level curves in the XY plane intuitively give you an idea of what this surface looks like. Now, as the surface gets steeper, what happens to the level curves? Do they get closer together or farther apart? Yeah, the level curves get closer together. That's right. That's right. And so it's nice to be able to look at a two-dimensional graph of these level curves in figure 4 and get an idea of what the surface looks like. Now notice also with the level curves they have these K values. Okay, so the K values tell you the different values of the function. Okay. And indeed, I think Ian had said this is like a topological map, and it is. Here in figure 5 is a map of Lonesome Mountain, and the 4,500, the 5,000, the 5,500. What do those stand for in that map? Elevation levels, that's right. And you notice that they skip by the same amount. Okay, they're jumping here by what amounts? The level curves, they're skipping by how much? Is it 1,000? 500, right? And you see they have to do that. The level curves, you have to skip by the same the difference between the level curves has to be the same difference all the way through in order for you to get the proper perspective in terms of how fast is this surface increasing or how fast is this surface decreasing. Okay, so that's that. Those are level curves. Level curves. Okay, are there any questions on that? Okay, well, let's move on here. Let's move on. So in the book, they have nice examples, but I want to go to figure 10 here. Okay, so here they're using level curves. They have h of xy equals 4x squared plus y squared plus 1. Okay, so let me ask you this. Let me ask you this. Well, all right. What they're doing is they graph a picture of this surface. And what is that surface? What is that surface? There. Yeah, it's a paraboloid. It's a paraboloid lifted up 1 unit from the origin, right? Paraboloid lifted up 1 unit from the origin. And they say that the graph of the surface can be formed by lifting the level curves. If you were, again, what they're doing on that paraboloid is they're cutting the paraboloid. They're cutting it at different levels, equally spaced. Okay, different levels are z-values. Different levels, equally spaced, and then take those cuts and project them down into the xy plane, and that gets you an idea of what your surface looks like. As we move out from the origin, so in figure 10, as we move out from the origin, are the level curves getting closer together or farther apart as we move out from the origin in figure 10? Okay, the curves are getting, well, are the curves, what's the word? I maybe didn't say this right. Are the level curves getting closer together or farther apart as we move up from the origin? Well, let's look in terms of the x-axis. It's easier to see the x-axis. It's getting closer together as you're saying it. And why is that? Why are those level curves tightening up? Why are they getting closer together as you move out from the origin? What's happening to the surface as you move away from the origin? The surface is getting, well, let's use the surface is getting steeper. That's what I'm looking for. The surface is getting steeper as we move away from the origin. So the level curves get closer together. Now, as we move into the origin, the surface gets not steeper, but shallower. That's right, Ian. And what happens to the level curves when the surface gets shallow? What happens when the surface is they expand, they get further apart. Okay. So far, are we good with this? Are we good with this? Who's comfortable so far? Sort of, yes. Okay, I'll take that. I'll take that. Okay. Well, let's go on. Let's go on here. So if we go on here, I don't want that. I mean, not yet. Man, hold on. Hold on. Just got to find my, wow, look at this. See what they've done there? They've taken surfaces, but they're functions of x and y, right? Do those surfaces pass the vertical line test? Do each of those surfaces pass the vertical line test in figure 12? Well, vertical line test for a function is what? Well, you know you have a function of x if you pass a vertical line through the function and it only touches the graph at one spot, right? So these are all functions of x and y. And there you have the level curves. Well, functions of x and y in terms of the z-axis. Yes, Ian, the z-axis. Z equals f of x, z equals your function of x and y. Good question, good question. They are functions of x and y. They are functions of x and y. Yes, that's right. And you see, do the level curves make sense? Actually, it's two pictures, right? Two pictures, two surfaces. Do the level curves, the graphs? Sometimes we call those contour plots. Do those level curves, do those graphs make sense? So for figure 12a, now Ian pointed out a good one moment here. Yeah, these are called contour maps. Contour maps. Okay, but the contour maps doesn't show. It tells you when the surface is getting steeper and when it's getting shallower, but it doesn't tell you if the surface is going up or down, right? So you see there in figure 12a, you got two hills and two valleys, right? In figure 12a, in that surface, you have two hills, okay, in the coming out of the what? The got to be careful here. Coming out of the let's see. Hold on. Sorry, class. I got to get my orientation right here. Positive x-axis, positive y-axis. So the valleys come out of the which quadrants? Really, we should say octants, right? Which octants? But let's just say the quadrants. The valleys come out of what? The first quadrant and the third quadrant. And the hills come out of the second and fourth quadrants. Valleys are below. Oh, yeah, valleys are below. And hills are above. Okay. Okay. How many of you have been in a valley before? A valley is like where looking up, you got mountains all around. How many have been in a valley? Like when you ski, a valley. I don't ski, but okay, all right. Ian knows a little what I'm talking about here. But the thing is, in Figure 12, in these contour maps, you're not given the values of the level curves, and so contour maps. It's helpful if you have values of the level curves. Yeah, now, functions of two variables are nice, but we can also deal with functions of three variables. So here you have a function of three variables, example 11. And yeah, We can find the domain of a function of three variables also. Okay, so in this problem here, well, the log of the log function is the one that's restricting the domain, right? The second part of this function of three variables that has x, y, and z in it, well, x, y, the sign of z, those are defined for any x, y, and z. But the log of z minus y has to be positive, so z has to be greater than y. Okay, and so that would be the half space consisting of all points that lie above the plane z equals y. So the domain is, if you wanted to picture it, it's a three-dimensional picture. Okay, one moment. Okay, so this is a little harder to visualize, but it is, it's in our calculus 3, right? They mention right here that it's very difficult. I'll highlight this. It's very difficult for three variables by since, whoops, hold on. Sorry, I got thrown out here. Hold on, let me get back here. Okay, can everybody see the highlighted thing? Okay, good. The ebook, good. So they mentioned, thank you, it's very difficult to visualize a function of three variables since that would lie in four-dimensional space, right? If z is a function of x, y, and z, z lies in the fourth dimension. But you can gain insight into a function of three variables by looking at what's called level surfaces. Okay, so level curves are when you set a function of x and y equal to a constant. Level surfaces are where you set a function of x, y, and z equal to a constant. And if you have a function of x, y, and z equal to a constant, you can actually graph that. So, and you can see how the function behaves. So a very famous example here is example 12. In example 12, they want you to find the level surfaces of this function of x, y, and z. Okay, and so what you do is you set that function equal to different values. Okay, and they show this in figure 13. Okay, so take a moment and look at that. So you see how the function grows outward. By looking at the level surfaces. It doesn't, no, it doesn't have surface area as we know it, Ian, because our surface has to be in three-dimensional space for us to compute the surface area. But I'm not saying that, if you take like a higher level math, they might have surface area defined for something like this. But let's see, Ellie says figure 13, good question. Figure 13, Ellie says, is equivalent to the two-dimensional graphs we were looking at when we had a function of two variables. That's exactly right. That's exactly right. All right, so are there any questions on this? This is really the so the intro into chapter 11. Okay, are there any questions at all? Okay, I'm going to stop the recording.